Well, today I'm joined by my good friend, Dr. Brian Keating. Hey, Brian, how's it going?
It's great to be with you, Fraser. How are you?
Good, good. It's been a couple of years since we talked last. Have you won any Nobel Prizes in that intervening time?
I did not, which is a good thing for sales of my book. If I win the Nobel Prize, I have to put out a retraction to the book, which is quite awkward. If anybody has ever
Yeah.
tried to retract a book, it's pretty damn hard.
Yeah, nobody wants to do that. So that's probably best that you don't win a Nobel Prize
I did win
ever.
Best Father. I did win Best Father this past June. So
Yeah. Are you sure? Did the Planck satellite perhaps provide some kind of counter evidence?
that's right. They found, there was space schmutz dust. Oh, by the way, Fraser, so for your audience in the US only, I want to do a special giveaway because you have the best, well, second best audience in the universe. Come on, I got to
Yeah,
give
sure.
credit
Fine.
to
Yeah.
but for your members in the US, I'm doing a giveaway to the first 100 people that sign up to my mailing list at briankeating.com/list. I'm going to send them the villain of my last book, which is a piece of space dust, a tiny little meteorite.
That's awesome.
Could be sent to anyone, but not in dangerous Canada. My
No,
my shipping department does not allow me to send and
no,
export to the Great White North.
no.
But if you're in the US, you can enter briankeating.com/list and you may win one of these 100 meteorites.
Fantastic. I've got I don't know if you can see it behind me, right over there. I've got a 1 pound iron meteorite. I'll grab it.
Oh, well,
Hold
your
on.
bocca is so luxurious and
Yeah, I know.
lush.
Hold on 1 second. I'll just
Very
grab it.
hard to.
Oh, it's time to start to get
Nice.
a little weather.
That is okay. People out
Windows.
there, that is substantially larger than
Yeah.
what you will
So,
receive. You will receive the logarithm of that if you win a little pieces. But it's the same one. Yeah, it's from Argentina. It's Campo de Cielo,
yep.
probably.
Yeah, it's Campo de Cielo. Yeah.
Yeah. Yeah,
Yeah.
those are wonderful and they're highly magnetic susceptibility. And you can play around with a magnet and you'll get some goodies and learn
I
about meteorites.
love, yeah, I love having meteorites, metal meteorites. It really feels like a chunk of space metal. Now,
Yeah.
I give them away to people too, and I tell them that it gives them a superpower. Like, not a really powerful superpower, but something that is, a mild superpower. Like maybe it won't rain when you go on mountain bike rides, that kind of thing. So,
That's right. You will avoid a derailer accident,
yeah,
on
yeah,
your next downhill trip. Yeah,
yeah.
I mean, if nothing else, you can impress people at cocktail parties when they start resuming again after the
Right.
pandemic.
All right. So, for people who don't know who you are, like the problem with us having talked many times is we know who each other is, but people might not know who you are. So, who are you and what do you do?
Yeah. So I am an experimental cosmologist. So I work on hair and nails.
That's
I
right.
treated Fraser, I made his haircut what it is today. Why he's
Yeah.
so famous. His beard is the next, or his goat beard is on my list. No, so I'm not a cosmetologist, although the prefix is the same. It of course means beauty in Greek, as many of you know. But I am not a an experimentalist in the classical sense, like my biology friends are experimental biologists. They can go down to the lab and take a frog and do some experiment on it and see if it doesn't happen or does happen to a control frog. I don't know what they're doing over there in the
Yeah.
biology department. I'm actually, the dean's got to take a look at those guys. um, but what we do is we build telescopes and technology and detectors and deploy them all over the world to sites never before really utilized for capacity at this level, including the South Pole, Antarctica, including Chile and the Atacama Desert. We are operating with my colleagues and friends in the Simons Observatory, not only the world's highest observatory, but the highest construction project. We have to build these telescopes, thousands and thousands of tons of material and earth that have to be moved around. We have to build it. We have to move it. We have to design it, power it. Imagine getting all the diesel fuel up to 17,200 feet. And then we
Ugh.
have to get the data and analyze massive data set, all in the service of trying to understand empirically observation. That's what science is, right? And you've had on many lovely theoreticians. Some of my best friends are theorists. I don't know if I'd let my daughters marry one, but they're really good friends
Yeah.
of mine. Brian Greene, Michio Kaku,
Yep.
I was just talking to Sir Roger Penrose on my podcast, which is my night job, I guess. I don't know. I'm a podcaster, YouTuber. Try to kind of learn as much as I can from Fraser and all the awesome work you do. You guys do at Universe Today. You guys really do a wonderful service to the community. And I felt, as a paid scientist, paid by the community of taxpayers, at least here in the U.S., and supported at a public university here in California. I'm a state employee. So I started to think, how can I give back to the people that pay my salary? And one of those ways is to do outreach in the spirit of a Fraser Cain. So I think part of that gives me the joy that I don't always get to receive when I'm talking to a contractor about why the diesel delivery, was late and this concrete didn't cure. Those are conversations I have to have, but conversations I want to have are like these and with my guests. And I realize many of them are theorists. Theorists get a lot of attention. They get a lot of notoriety, that there's, new theories, wormholes, black holes, other kinds of holes. And maybe there's parallel universes, multiverses. We'll talk about some of that. And maybe there's new particles and superstrings. And I've had on all those folks. I've talked to 14 Nobel Prize winners. And most of them were theorists, but not all. And to me, I wanted to get out there to a young Brian Keating or Brianna Keating, that you can build stuff that takes the data, that allows these geniuses to do the theoretical investigation, to not prove their theory right. I think that's a huge misconception. I'm not in the job of proving your theory, my theory, or anything right. I'm in the business of proving everything else wrong. Mm-hmm. And that can only be done by having data, and the data only come from telescopes of the kind that my colleagues can build.
And I think, the experimenters are the unsung heroes of the science world. Really, the theorists and the experimenters work hand in hand, but people don't know what the experimenters are doing. And yet the day in, day out, the hard fought, hard won victories in science often come by the results that come from the experimenters.
Yeah. One of the most successful ways you can approach science as a practicing scientist is look for inconsistencies in what's already known. For example, the inconsistencies of the orbit of Mercury led Einstein to think about the theoretical implications of general relativity. But he wouldn't have had, those data to even stoke his imagination had there not been very accurate telescopes and data built by very deep thinkers and constructors and project managers and leaders. It's just a different type of physics. It's as different, I think, as, say, a theoretical physicist might be from a biologist or something. It's almost a different occupation. And it's just, we put the adjective experimentalist or theorist in front. But it is true that theorists kind of get all this glory. And I think of it kind of as, I tease my friends who work on software. I can program BASIC, or, I can, do those Swift Studios to make an app or something maybe. But I'm like, theory is kind of like software. Like, it's very easy to make a ton of software. You could just make an infinite loop, to make a stupid example.
Right. Generate a bunch of data. Yeah.
But to build an experiment, even like a simple one, it takes a lot of hard work. And I'm not making value judgments at all, but I want to give people a glimpse into the daily life of it. That was my first book, Losing the Nobel Prizes. What does it feel like, a memoir, to approach the greatest, questions in science? Did the universe have a singular origin? Are there multiple universes? What is the nature of the types of alternative models, from the microscopic to the macroscopic? And that gave me great joy. But, it's also kind of this niche that I don't think many people talk about. So a lot of what I'm doing on my YouTube channel, Dr. Brian Keating, is to go through the latest and greatest experiments, not done by me. Sometimes I'll bring in some footage from me in the lab or my students in the lab, but oftentimes it's something totally different. The lifetime of the neutron. We didn't know the lifetime of the neutron to better than a few seconds. And we used to think about the Higgs boson, which could last for, a trillionth of a second. We didn't know the age that the neutron gets to in ripe old retirement before it dies, to better than a second, a part in 1,000 or worse. So I did a video about that experiment on Long Island and other places. And it's just really fascinating to explicate it in a way that a young person can appreciate, or even experts in the field. And so that's kind of what I do as an overall worldview.
All right. Well, enough log rolling. I'm going to put you to work now. So in terms of experimenters, astronomers have gotten one of the most powerful experimenting tools, instruments in their hands in the form of the James Webb Space Telescope. And we've gotten a couple of months of experience working with James Webb so far. From an astronomer's point of view, and especially someone who really studies the early universe, I mean, your focus is the cosmic microwave background radiation, the evidence for cosmic inflation. That's a little earlier than James Webb, but I'm sure there are implications. So what has been your experience with James Webb so far, just in terms of, in the science that you're seeing coming out of it so far?
Yeah, I mean, actually, not very much of what it's done has had, direct implication for the exact type of science that I do. Just taking a very big step back, we think the universe began in an incredibly hot, dense phase. We don't know if that was a singular one-time event. We don't know if that was a singularity, a quantum divide by zero error, where there's infinite amount of energy density or matter density. We don't know. Those are open questions of the type that the cosmic microwave background can explore. But Webb can't really say that much about that phase in the universe. What it was designed to do is kind of be a Hubble Space Telescope with redder filters on it, with higher resolution, more massive telescope. But as you build a telescope, you have to be cognizant of the size of the objects you're looking for, how far away they might be, how near they might be, but also what the expansion of the universe will do to those objects. So while it's true that Hubble's early observations of the galaxies and their recessional properties of Estes Slipher and others, those did have an implication for an origin story, a cosmic Big Bang, later to be called. But it didn't necessarily have, and it's make anything quantitative about how the universe actually began. So to separate what Webb does and what I do, Webb is looking for, actual objects. What I'm looking for are not objects, but they're more properly called structures. They're loosely bound conglomerations of ordinary matter, dark matter, light, neutrinos, and other types of properties that, because it's the oldest light that we could ever hope to see, it originates from 370,000 years after the fusion of the elements, which some people incorrectly, conflate with the origin of time or the Big Bang itself. Really what astronomers and cosmologists mean is, when do the elements form? Because that's the literal first time we had fossils, we had hard evidence, we had chunks of matter, if you will. Yeah. To actually look at and compare with what we see today. We could actually do that in a quantitative fashion. After that comes the cosmic microwave background, which is followed by an epoch of extreme boredom and darkness, a plasma of unimaginable, lack of fecundity and lack of interesting objects, kind of like, well, I was going to say, some parts of northern Saskatchewan, but I'll say some parts of the Mojave Desert down here in California. It's just flat, barren. There's little ripples in it, but other than that, not very interesting. And then the universe lit up. Then it began producing stars and galaxies. And then much, much later, planets and people and podcasters. And where Webb comes in, not on the podcast side, but we'll probably get to other aspects, but really this bound structures, and including what's the most interesting thing that I'm hoping for from Webb, since I don't use it, I can say what I want to see from it, is evidence for life in the universe. Because I'm actually very pessimistic that there's life, let alone intelligent life in the universe. We can get into that later. But I'd be very open to it. And I think a good scientist should be open to all these different ideas. But in terms of what it can say about my day job, it's not really a threat to my employment.
But aren't there implications? Like you say, you're looking for structures, these large scale structures in the universe that are demonstrated by the fluctuations, the density fluctuations, temperature fluctuations in the cosmic microwave background radiation. Don't those evolve over time to the larger scale structures that we know and enjoy today? And won't Webb be able to try to fill in the missing pieces from there to now?
It will fill in some of the missing pieces, but mostly what it's doing is an astrophysics experiment. It's exploring how did the gas that was left over when the universe, finished making the plasma and the hydrogen and the helium and the cosmic microwave background plasma, that cooled and condensed until it became ionized. So really nothing much happened for millions of years, hundreds of millions of years. But the actual import of it, it's kind of like looking at a frog. Let's go back to my biology friend. So you got a frog, that's a biological structure. If you studied it, and let's say you even understand how it evolved, it comes from a tadpole. The tadpole comes from a sperm and an egg cell. I don't know how PG-13 we can keep it here. But anyway, it comes from mommy frog. Yeah, mommy frog and daddy frog, right? But you couldn't necessarily say by watching the evolution. Let's say Webb pushes us from the mature frog of Hubble to the tadpole phase. It really wouldn't tell you much about the origin of life in the universe, or even of the theory of evolution, or even of DNA, right? I mean, we had frogs for thousands of years that people didn't uncover DNA. So we have to make a distinction. One is a predicate on the other. I don't need what Webb's doing to do what I'm doing, but it can be looked for consistency checks on certain things. But here's another example. And of course, hopefully we'll get to this. There's a huge manufactured kind of clickbait controversy going on, courtesy of just one, team or type of player who's been doing this since the time of the Hubble Deep Field in the 1990s.
Yeah, 92,
even wrote a book called The Big Bang Never Happened in 1991. Before the Hubble Deep Field. So we'll get into that because he has a new video out today where he's attacking me on his channel.
Well, I like that term, the manufactured clickbait. It is funny. Well, so let's get into that right now then. The discovery that is being made in the images that are coming out from Webb, that it is seeing galaxies that are better evolved, more fully evolved, more modern looking than the kinds of galaxies that astronomers were hoping to see. So is that true?
Well, I wouldn't say hoping. I would say maybe expecting based on previous data, right, which came from Hubble, right? So the first question I asked when I saw this paper, and actually on my video, I did a one solo video about the paper when it just came out, or the article in this IAI newsletter or the website. And then I did another one with Professor Geraint Lewis down in New South Wales in Australia, or Sydney rather. Yeah. And we're good friends. And we went through it. And then on that video, the lead author of the paper, Leonardo, of the paper that said panic at the disks, which is obviously like a joke, he is like commenting on why it's irrelevant what his team show. I mean, you think a scientist would be really cheerful to know, look, I've overthrown this notion, the Big Bang has these problems in it, and I'm the first author on this first paper to really. No, nothing of the sort is really true, because a lot of the data that is seen there is 100% consistent with what Hubble saw. In other words, Hubble saw formed galaxies at high redshift. It couldn't go as high a redshift because it didn't have the infrared filters that James Webb has, but no one was taking seriously. In other words, this paper this article that claimed the Big Bang never happened could have been written, 10 years ago. In fact, it was written 10 years. Every 10 years, it sort of comes out. Why does it keep doing that? Because we keep getting better and better, more and more accurate data. And to quote, I think it was John Maynard Keynes, when the facts change or when the evidence changes, I change my mind. What do you do, sir? Meaning that he's basically ascribing to the Big Bang features that have no pertinence to it on a professional astronomical scenario. And worse yet, the most fundamental observable in cosmology since the beginning of cosmology as a quantitative science, thanks to Hubble, is redshift. And there is only one thing that the models that are being proposed that so-called prove the Big Bang never happened, the one thing they cannot account for is redshift. In other words, the most crucial observable is being completely ignored or not understood. And the very highly accurately studied data by professional astronomers is being laughed at and called into question as if it disproves the Big Bang itself. So again, getting back to the analogy of these frogs, it's like now we see a tadpole, and the claim is being made that DNA doesn't have a double helix structure and that Darwin is incorrect. There's no evolution. When it may be true that DNA is wrong or that the evolution is wrong, but these data say nothing about it, because merely what's happened, and I say merely, but it's a tremendous amount of work. Webb can see back, say, twice as far in time. So when these galaxies were hundreds of millions of years old, 200 to 300 millions of years old, and Hubble saw when they were 5 to 600 million years old. If that constitutes a crisis, I think it might be good for certain people to see a therapist about this, because it's really not a crisis whatsoever.
But I mean, you as a scientist, you're delighted when when you discover that you're wrong, because now you're closer to being right.
That's right. And I made the analogy in a couple of conversations I've done so far. It's kind of like the flat Earth, right? If you think the Earth is flat, you're wrong. If you think the Earth is a perfect sphere, you're also wrong, because it's not a perfect sphere. It bulges at the equator. It has a little bit pear-shaped nurple on the top. I don't know. But it's not a perfect sphere either. But you're less wrong, as Asimov used to say. You're less wrong if you think it's a sphere than if you think it's flat. And putting all these things on top, as I said, a good thing to do is to look for inconsistencies. So there truly would be no one more excited than a professional cosmologist to learn that the Big Bang is missing. And we know it's missing things. No theory is complete. But when you point to inconsistency, so here's a good example that I think we might have even talked about a couple of years ago when I was last honored to be on, and that's the Hubble tension. And I've had on Adam Rees many times and Brian Schmidt and others on my podcast. We talk about it. And what's the crisis? The crisis there is that the cosmic microwave background measurements done by Planck and WMAP reveal a value for the Hubble constant that is about 68 in these weird units of kilometers per second per megaparsec. The measurements done by Adam Rees and his team using the Hubble telescope and Cepheid variables and Wendy Friedman's group and Tipper the Red Giant branch, they advocate for a slightly bigger value of the Hubble constant. Now, why is the Hubble constant important? Well, it's really how you get the redshift, which I said earlier is the most important number in cosmology, observable in cosmology. So you want to construct the redshift distance relationship, and the proportionality constant is Hubble's constant. It also gives you a handle on the age of the universe. The reciprocal of the Hubble constant has units of time. Kilometers divided by megaparsecs is dimensionless, and then you've got these seconds per second. So it ends up telling you the age of the universe. Now, these two experiments are off. One says 68, one says 72. They're off by a factor of 4 in these units. It turns out to be about 9% discrepancy. That is incredible, that you can make a prediction based on what the universe was like when it was 380,000 years, propagate that forward 13.8 billion years, and you agree to within 9%. And none of them are saying that the Hubble constant is effectively 0, because that would be a static universe, and none of them are saying it's infinite. We have an exquisitely calibrated and accurate knowledge about how fast the universe is expanding, and two different methods disagree. And that is a reason. But what was that a reason for? It's a reason for excitement.
Yeah.
It's a reason to go deeper, as you say, to learn more about why this is happening. It's a fascinating time to be alive. And it'll turn out one of them is right, one of them is wrong, or it'll turn out there's some new physics that we didn't understand.
And that's the most exciting one. Like, I think of all the choices, like the one you're like, we don't understand what the universe was doing at different ages, or we don't understand all of the factors and variables that are feeding into the expansion of the universe. That is exciting. And it's weird to me, like for you as a cosmologist, to receive messages from people who tell you that you're being closed-minded because you won't accept change and new theories and so on, has got to be exhausting, because you can't wait to change your mind. You can't wait to get new evidence. The problem is not the excitement. It's not like you're being dogmatic about the theories as you understand them. It's that the counter theories have failed to deliver the evidence that is necessary to make you change your mind.
That's right. And in fact, in this case, it gets worse, because Mr. Lerner, who's just a private, individual, he does operate a fusion research company, which is always mentioned for donations, and yet his audience will always condemn scientists like me for taking grants from, private and public funding agencies that are based on peer-reviewed submissions in the, kind of eternal tradition of science, which is to have advocacy, but also have some bit of contentiousness, but doing it respectfully. And instead, I used to, before I met this Mr. Lerner virtually, I used to tell my students, if you ever find the words coming out of your mouth that this referee report is treating me the same way as Giordano Bruno, then just shut up, because it's laughable to be that level of grandiosity takes a level, as we say in Yiddish, of chutzpah. That is not appropriate when doing science. Compare yourself to Bruno. So this gentleman, Mr. Lerner, compares himself to Kepler, and he compares others of us to Ptolemy, which is really quite rich because as I said, he is advocating and has a pitch for money at the end of all of his, and there's no oversight over that. I mean, I thought I had heard that he had raised millions of dollars at one point for this fusion research. But again, he's advocating for a model of the universe that's not new, Fraser. It's incredibly ancient. It's a static universe. It's an unchanging universe, which then has to grapple with the plethora of literally billions of observations that are not only consistent with the universe not being static, but being completely dynamic, evolving, changing, rich, full of interesting features and things to study. So he literally cannot explain billions of observables. He admits that. He says, I have no explanation for redshift, but I'm confident that in 200 years from now, that they laughed at they use Ptolemaic epicycles, you guys are professional cosmologists are using expansion hypothesis. So it's kind of fun to debate him virtually online. But there's a limit to how seriously you can take something that's 2,000 years old plus.
Yeah, and it would be nice if it could be kept civil, and it's sad to me that it's not. It's sad to me. It's weird to me that, like, everybody loves space. Everybody's enthusiastic for space. I keep noting this, that it's just like you never run into a person that isn't into space.
I know.
And yet,
I always say, Fraser, I love astronomy because it's not political. Like, there's no Republican asteroid.
Yeah.
I don't know what you have, liberals up there or whatever.
Yeah.
There's no liberal comet or, it's apolitical. It's a safe space for intellectual growth, right?
Yeah. And yet people do bring kind of, I don't know, they get wedged in their worldview and lash out, which is weird to me. So you, as a practicing cosmologist, you are steeped in the latest findings, the latest information. What are the challenges that cosmologists are wrestling with right now in the earliest moments of the universe that maybe the public audience isn't sort of up to date with and familiar with? What are the really interesting things that are happening right now in the field?
Yeah. And I should say, as it often is overlooked, that there are, kind of lacunae or gaps in our understanding, things that we lack an understanding of. Things like dark matter and dark energy. This is frequently trotted out by the Big Bang deniers, saying, oh, well, you guys make up this fantasy substance called dark matter and dark energy. And I've always retorted to them in a couple ways. One is to say, yes, it's true. We haven't directly detected all the dark matter that we know exists based on multiple forms of evidence, but we have evidence for dark matter. We've made exquisite detections of its gravitational influence, and we actually know of one form of dark matter that we've detected here in the laboratory on Earth. It's called a neutrino. It's a weakly interacting massive particle, so we know that that's a form of dark matter. Happens not to be sufficient to close the universe and to make it flat, rather. But in this case, they would have said, 20 years ago, 30 years before we had evidence for neutrinos being massive, they would say, oh, that's just, another Ptolemaic epicycle you're putting on your theory. So just because you don't know something now, I think it's entirely anti-scientific, not just bad. It's anti-scientific to say that you don't know something now, so you'll never know it.
Yeah.
And one of the most important things that we are looking for in my field is really to understand the earliest we could possibly understand. I always joke, my job is to find out what happened on the Thursday before the Big Bang. Because that question is either poorly defined or undefined, as Stephen Hawking used to say. It's like asking what's north of the North Pole. But scientists discovered what's north of the North Pole, Fraser. As you know, closer to the North Pole, there's Santa Claus, right? So we know there's so Stephen was wrong.
Sure, I'm gonna sign on to that theory, but I'll
All right.
yeah,
Okay.
yeah.
All right. Fine. But
Don't send it
but
to me for peer review. That's all I'm saying. Yeah.
But there are very well motivated theories that posit an existing universe prior to our universe, either in space or in time, like a previous universe that collapses in a big crunch, or a universe that is parallel to ours in space and time in what's called a multiverse. And these things are testable using the tools of cosmic microwave background polarization for the very first time in scientific history. And I find that incredibly exciting. So the most kind of exciting thing to me is also kind of not really appreciated by the lay people that might be in your audience or my audience, and that's that there is a controversy on whether or not there was actually a universe that pre-existed our universe, and it is come a long way. There's a lot more research into what's called the inflationary universe that we spoke about, and that's the big part of the subject of my first book, Losing the Nobel Prize. That book was about this experiment here at the South Pole, if you're watching, called BICEP, which I designed and built along with my colleagues at Caltech and Harvard and University of Minnesota and Stanford. And that project initially announced evidence for inflation. What is inflation? Inflation posits a quantum field that's sort of eternal, like exists forever in a vast space-time, in all of space-time. And that universe had a big fluctuation in the inflaton that caused it to inflate and expand at superluminal velocities. And now that event could leave an imprint on what's called the polarization of the microwave background. And that polarization is exactly what we study. So for those of your viewers who might not be familiar, I said I love to do experiments, Fraser. So a polarimeter is very simple. It's a telescope. In our case with BICEP, it was a refracting telescope. And it has some kind of what's called polarizing filter. It has something that solicits only one polarization, allows only one polarization to propagate at a time. And if you have an identical one, you'll see as I rotate them 90 degrees and then 180 degrees, the light that gets transmitted, if you're watching on YouTube, you'll see it go through a complete darkness. Now it's getting more and more transparent. Then it gets completely dark. And that happens twice for every physical rotation of one of the two polarizers. That is the sine qua non, the hallmark of polarization. So you attach one of these to a telescope, and then you rotate the telescope, and to whatever extent you see the pattern of light's intensity increasing and decreasing twice for every physical rotation of the instrument, you get a measure of its polarization.
And so your telescope is actually rotating? Yeah. Physically rotating is it like making an observation and then it's rotating and making another observation, or is it
100%?
That's right. Really cool.
That's 100%.
Yeah.
And we have multiple. We also have something that we got from a very expensive source of rotation, and that's God or Mother Nature, if you will. So when the Earth rotates, imagine that the first quarter moon is rising. Okay, so it's rising. So half of it's illuminated, and there's the lunar terminator right above the horizon. Throughout the night, that terminator rotates around like this. So the rotation of the Earth and causes the modulation of the angle of the terminator. The same thing happens with the polarization of the microwave background. So we have God's or Mother Nature's own polarization rotation mechanism. And then furthermore, we can also employ certain types of crystals that you get from your astrologer friends. And these crystals also rotate the plane of polarization. They're much, much smaller. You can put them right at the focus, if you like, of the telescope or about there, and rotate them extremely fast because they're very small. So you can see and disentangle the effects of true, honest to goodness cosmic polarization from instrumental effects or other sources of spurious polarization. And in so doing, we hope to make a map. You've undoubtedly seen the colorful maps of the CMB's temperature. We want to make a map of its polarization with enough sophistication to see whether or not there are waves of gravity, not just waves of light, not just waves of matter or density perturbations in matter, but if there are waves of gravity like LIGO detected that cause the shearing and squishing and squashing, technical terms, of space and time itself. That will only happen if and only if inflation took place. There's no other mechanism to generate these waves of gravity. Therefore, it provides a very crisp test for those that do not believe that inflation took place. Even they, like Paul Steinhardt, who's the Einstein professor at Princeton, Anna Aegis, who's a renowned postdoc at NYU, and many others around the world have looked at Sir Roger Penrose, Nobel laureate. They have alternative cosmologies, and they all admit if we see this type of polarization called B-mode polarization, it will kill their theories dead in the water.
Now so you actually have a preference in this. I mean, obviously as a scientist, you're going to let the evidence take you wherever it goes, but your hunch is that you won't be able to find this polarization. Am I right?
No, I don't think I've said that. I said I don't think we'll find life in the universe or technological life.
No, but like as you said, like you're more on board with the Penrose idea of a cyclical universe than other origin.
I wouldn't say that.
No? Okay.
So what it comes down to is the excess of evidence that we have currently very highly suggests that inflation took place. But it's kind of like circumstantial evidence. Like you come to a crime scene, you see a dead body, there's a gun, the gun is warm, but there's also a knife in the room. But versus coming into the room and you see like the person, the criminal, and the gun is smoking in their hand. So these waves of gravity are incredibly precise and very crisp in the Occam's razor sense, discriminators of whether or not the universe began with a singular. So inflation is almost synonymous or concomitant with the Big Bang and the singularity. It's very, very closely attached to that. Whereas these other forms of the universe, origin, cosmogenesis, they don't have really require any singularity in space-time itself. So it's fascinating to me. I'm actually, for the first time in my life, I am agnostic. It is true that before, when I was, a young scientist, as I recount in this book, I really wanted to win a Nobel Prize. I wanted that at all costs. I had a very tumultuous relationship with my father, who was a great mathematician. He'd done some theoretical physics, won incredible prizes, and was the youngest full professor at Cornell at age 27. And we always had this rivalry. But the one thing he never won was the Nobel Prize. And since I came up with this idea to test the gravitational wave origin in an inflationary process, thanks to my colleagues in theory and other places, then I thought this was my sure ticket to win a Nobel Prize. So yes, in that sense, I was very much kind of motivated by non-scientific reasons. I'm not especially proud of that, but that's the truth. I was, it's the highest award, not only that you can win, I think in science, but I think in society as well. I mean, every 4 years there in America, at least we get, 70 Nobel Prize winners tell you to vote Democrat, or the Iran deal is a good thing, a Nobel Prize winner here. And so you don't see that in like Olympic hurdlers who have won gold medals all say to support the Iran deal. No, you don't see that. So it's much more kind of disproportionate. And that was part of the unscientific reason I had, as I count, this book is mostly it's mostly a memoir of what it feels like to be a young physicist trying to make a name for him or herself and building things as opposed to theorizing things.
Right. But I guess, I mean, the impression that I got is that you have and you say that you're agnostic today. When we talked a couple of years ago and when I read the book, I got the impression that you had a preference, just in the, a preference for, in like coffee versus tea level preference, a preference for a non-inflationary universe. And I guess by proving inflation correct, you would win by getting a Nobel Prize and making an incredible contribution to science. And by failing to prove inflation correct, you would also win by essentially your preference continuing to hold and there being a glimmer as that being a possible source for the universe.
Yeah. I mean, some of that needs to be unpacked. I think the primary reason why I'd like to see something is because the alternative is that you see nothing. And, when you see something, like imagine you just never detected the Higgs boson because you could never build something as powerful as a Large Hadron Collider. That doesn't mean that the Higgs boson doesn't exist. It just means that you couldn't build it, or that the energy scale at which it's produced is far in excess of what could be measured with human technology. Would I be disappointed if I built the Large Hadron Collider and I didn't see anything? Yeah, because you always want to see something. A null result, which is what it would be if we don't see anything, and what the BICEP result turned out to be. So we actually saw this play out where we made a detection, claimed it was real, was whispered about for winning a Nobel Prize. And I should also say that concomitant with the inflationary paradigm is the multiverse. There's basically no way to suppress the formation of other universes in the vast space-time that we used to call the universe, but is now called the multiverse. There's no way to shut that off in the inflationary paradigm, and therefore you have what's called eternal inflation, where inflation is occurring in these various pocket universes throughout the cosmos. So the stakes couldn't be higher if you were to detect it. That is true. On the other hand, it brings up a lot of problems too, because at least in our universe, it would mean that time began. Which is a weird thing to think about, right? We think about time and entropy as the change in measurable quantities in something. We think about it, as Einstein used to say, very helpfully, time is what a clock measures. But you need change. Well, how do you get change if literally in the before time, there was no time? In other words, it's like time emerges into reality as a new property that we take for granted now.
But doesn't a cyclical universe just push the problem back one iteration?
Does which universe?
Like a cyclical universe. Like if there was a universe before this universe, don't you then have to ask yourself where that universe came from, and then the universe before that came from? Like at a certain point, don't you still end up with the same problem, which is how did you go from nothing to something?
Yeah, unless you know that there's either a single origin of the universe, as a naive interpretation of the Big Bang would posit, or that there was only one cycle of the universe before our universe began, then you would be right. And in fact, in most theories, it's not necessary to support that there's an infinite number of them. But in Sir Roger's theory, there are. He calls them aeons. And Paul and Anna's theories, it's not specified what they are, merely the properties they'd have to have. So yes, in a sense, it does. It's kind of like the question of who made God, and in kind of philosophy or theology.
Yeah. So I guess why is that comforting? Because for me they are exactly equivalent. Like if you say, okay, the universe had a beginning, that's weird and unsettling. And so a less weird and unsettling idea is that there was a universe before this universe, and that one died and this one formed, and after this one dies, a new one will form. That still doesn't resolve the issue for me.
Yeah. So
from an emotional standpoint, right?
Right.
Right.
But there's another issue, which is the multiverse, and there's an allied concept in string theory called the string landscape. And these are really kind of mind-expanding concepts. In one, the supposition is that the universe has an infinite number of parallel, or effectively infinite number of parallel copies, each potentially with different laws of physics. In the string landscape, it suggests that there are regions of space-time that have different vacuum states and different values for the constants of nature, et cetera, et cetera. And I think what the opponents of the inflation and therefore the multiverse paradigm suggest is that if you have an infinite possibility, if I'm hosting Universe today and you're honored and blessed to host Into the Impossible, then anything goes. I mean, literally anything goes. Any combination of events can happen. Any combination of constants of nature. I've often speculated, if the laws of physics and even the constants of nature can change, and even the number of forces can change, what prevents there from being changes in the laws of predicate calculus or logic? Or, does, if A, then B, and A not imply B, in modus tollens in another universe? It seems to be nothing that would stop it if you can create new laws of physics, which are physical manifestations of mathematical concepts. Surely you could create new mathematical structures. As Max Tegmark suggests, all mathematical structures exist in his level 4 multiverse. So there are people like Paul who find that distasteful, because then it is really possible to lose predictive power of a theory. If anything can happen in the overarching theory of the multiverse, then our measuring one aspect of it would be no more satisfactory than, say, the anthropic. I don't know about you, but I don't really care for like anthropic reasoning very much. It's certainly in the weak form of the anthropic principle. And so I think it's
Wait, so hold on, you don't care for the weak form of the anthropic principle?
well, to say that, it's always seemed very tautological is all.
Like we wouldn't be here, like if the universe didn't support human life, we wouldn't be here to observe it.
Correct.
Right.
Yes. And, that's true. But does it give you anything to predict? Can it tell me something about the mass of a particle or the location of a galaxy? Or no, it really can't. And what we would like, and all physicists, I think, admit this, we don't know why the electron has a mass of 511 kilo electron volt. We don't know why. It would be great to have a theory that predicts that. Right. And if you were to say, there's a theory called the standard model, and let's say it could someday predict it, right? Let's say it comes up, but then you say that theory of the standard model is just a fluke of our particular instantiation of the laws of physics in our bubble universe. That then just that in your language pushes the problem back. Mm-hmm. And so there are people, and it's so fascinating, Fraser, because a lot of the initial resistance and the current resistance of these Big Bang never happened people is that they claim it kind of smacks of theology, that the Big Bang is like, and that's what Hoyle was, a huge atheist, and he came up with the name, the Big Bang, as a pejorative insult. But that's not scientific, right? He didn't believe that it sounded like Genesis 1:1, and therefore it had to be wrong because there's no God. That's not very scientific. But it doesn't mean he's wrong. It just means that it's not scientific. So I think there is something to be said for those that advocate towards the predictive power being the judge of a scientific theory, and in so doing, claim, I think, a little bit too often that a theory has to be falsifiable. So you really can't falsify inflation. That's a problem. Whereas, as I said, you can falsify Rogers' theory or the bouncing model because you observe B modes in the early universe. You kill those theories. It doesn't prove inflation. Again, it's the smoking gun. It's circumstantial evidence. But at a certain point, you get enough circumstantial evidence.
There's no way to falsify. Sorry, there's no way to falsify inflation. Like there couldn't be. Like there's,
Because if we don't, let's say inflation took place, but it takes place at what's called a very low quantum field energy. It will produce gravitational waves, but they'll be too small to measure. We'll never, and any conceivable technology due to what's called cosmic variance, where there's just too much random fluctuation in the different regions of the sky, we never know if it took place, even though it took place. Mm-hmm. So you can't prove it. And then if it took place, there's literally 500 different, forms of inflation. And you'd wonder, well, which one is it? Yes, it took place, but it's not as easy as an inverse mapping in mathematics from a value to a uniform definition, linear function. So I think there are reasons to think that from a Popperian perspective, where falsification is the sine qua non of good science, that you couldn't really rule out inflation, but you could rule out these other ones, which would give it some advanced, kind of precedent over the inflationary model. And as Steven Weinberg said, even long after the discovery of the CMB in 1965, he wrote in 1978 in the first 3 minutes his apocalyptic book on the early universe. Still a great book, and I recommend it to all my students. Even he wrote that the static or steady state universe is preferable. A, because it looks the least like Genesis, and he was a big atheist, as you know, but also B, because it could be ruled out. Whereas even he thought the Big Bang could never be proven, as we keep, debating about, right? We don't debate if I drop this crystal ball, if it's going to fall. Like I always say, I don't believe in gravity.
Right.
I have evidence for gravity. So that's what we want.
Right. But I guess aren't there, you say Roger Penrose, there are other physicists working on this, that there are alternative ideas for the formation of the universe that are different than the Big Bang. They solve the issues with the Big Bang, the lack of monopoles, the fact that temperatures are the same, et cetera, right? That, that's what inflation was designed to do, was to fill in the missing pieces of the Big Bang. And and these other theories do the same thing. Shouldn't they leave some kind of trace in the universe that there could be evidence built that those things are the case? Wouldn't that by having more evidence lead the theory. You're not disproving inflation, but you can never disprove a theory anyway. The evidence is starting to build into some alternate hypothesis.
Yeah, so so a lot of the work that's being done in bouncing or cyclic models is revolving around a more, I think, well, I don't know if it's more important, but it's a more technical question of whether or not you can have a universe that doesn't have a quantum singularity in it. Because the Penrose-Hawking singularity theorem suggests that in any expanding space-time, you reach a point of where you do obtain a singularity. But the caveat is often neglected that that's only in classical GR, and it's only on scales that we would consider macroscopic. So from that perspective, it isn't guaranteed that there can't be a non-quantum or non-singular origin of the universe. So all these reasons are of course fascinating. The more things your theory predicts, the better, because it gives you more things to hang your theory on, more hangman's nooses that it has to evade. And the more that it passes, like GR has passed, numerous hurdles, even hurdles that Einstein didn't think it would pass, like gravitational lensing, gravitational waves, expanding universe, which, by the way, you have to deny that the universe is subject to general relativity. In other words, we know that if you believe the Big Bang never happened, because the universe can either be either static, in which case it's stabilized by a cosmological constant, as Einstein blundered, right? Or it will have to contract or expand, depending on what the matter energy density is relative to the critical density. We know there's matter in the universe. We exist. Therefore, the universe should be collapsing unless there were some expanding force, like dark energy. To keep. So these people have to instantiate a level of either lack of belief in general relativity, which is past innumerable hurdles. I mean, it passes it every day in your cell phone GPS, right? A billion times a second. So I think it's extremely far-fetched, these notions that you have to give up so much to believe that. Now, it is true, we don't know, we don't understand what's happening in the earliest moments and what quantum gravity would even look like. But there's no guarantee that it didn't emerge from a classical collapse or a classical bounce. And that's what these alternatives are working on. And Roger doesn't have anything like that whatsoever. But they also, the weak spot, at least in my mind, I would love a theory that's an alternative that makes all the predictions or lack of predictions, in other words, doesn't predict waves of gravity that I could possibly detect with my colleagues, but doesn't feature either unknown forms of matter or energy, like the inflaton field. So the bouncing models posit a scalar field, a quantum scalar field, and that regularizes and controls the expansion and collapse of the universe. And in Roger's theory, he has these things called eribons, which are like dark matter, dark energy, who really knows? He has these magnetic fields, these Hawking points. And so there's all sorts of like new stuff. It doesn't mean it's wrong, but I would like something, no quantum field, no eribons, just protons, neutrons, my favorite particle, the crouton, which I'm going to grab soon for lunch, and really went deep into that kind of something. It'll be look as different from inflation as is possible to imagine. But so far, I think it shows that my theoretical understanding should be, left to trying to predict, horoscopes and stuff, and I should just stick to being an experimentalist.
Yeah. From my perspective, I think you've softened. That's my impression. Talking to you a couple of years ago, I think you were less ambivalent. If that's a thing that's possible, I guess. You had more of a position that you held. And the impression that I get now is that you've become a little more ambivalent.
I think I agree with you, Fraser. I think it's more of a condemnation of my, I know it's great to be like, this is definitely true and you're an idiot if you don't believe. I mean, I know that, but I think a scientist, at his best or her best should be kind of ambivalent. I mean, there's so 100%. Many ways that confirmation bias snuck in. So I guess it's a condemnation of my previous self, which is fine because I've grown. I like to think I've grown in more ways than just physically gotten bigger during the pandemic, but to think that, but to appreciate it more. And I think partially, people like you and people like you have really inspired me that there is so much kind of, there's so much, I don't want to say like nonsense. There's so much non-scientific stuff that's out there. And I always feel like we scientists are given this script. It's like all we have to do is read it and we'll win an Academy Award. Like, we have this wonderful script, and so few of my colleagues do anything like what you do or what I'm attempting to do, or, you know, my friend Sabina Hassenfeld or Arvin Ash, all these guys and gals are doing. And it's so important to do it. And I feel like in no other form of society would you have it be acceptable. If they, you know, I quit my job, you know, one of my students, former grad students, she works for Amazon. And if she said to Jeff Bezos's replacement, she said, like, you can't understand what I'm doing. I'm very specialized. I'm very sophisticated. I'm doing things that are so beyond your comprehension. By the way, I expect my paycheck on Friday. Like, she'd be fired in a second.
Yeah.
And yeah, we kind of do that. We kind of say things like, I always joke about Feynman. You know, there's this one quote where he says, you know, he says, if you can't explain it to your grandmother, then you don't understand it.
Yeah.
And then when he won the Nobel Prize, a reporter asked him, what'd you win it for? He goes, if I could explain it to you, it wouldn't be worth a Nobel Prize. So, like, which is it, Richard? But he did say, you know, the most important principle is not to fool yourself. And the second principle is you're the easiest person to fool. And I think I was a fool. I was a fool in the sense of Feynman. Like, I wanted to see this. I wanted to win a Nobel Prize. This is my quickest, maybe only shot at winning it. And now, like, it's so interesting because I started my podcast, you know, probably since we really talked in earnest. I've talked to 14 Nobel Prize winners. And it's not like, you know, it's this whole, you know, combination of things. Like, you really don't want to trade your life with anyone, Fraser. Like, you don't want to say, oh, I wish I was Mr. Beast of science or Joe Rogan, or like, no. Are you going to take everything that they're dealing with? Are you going to, like, suffer through all the things that they have suffered from and, like, deal with it? And no, you don't want their problems. You don't want anything but your own.
But I think I think the key is that as a scientist, your job is to search and you're on these journeys of investigation. As a journalist, which is what you are as well, your job is to listen and to, he says after interrupting you, your job is to listen. Your job is to let the person talk, and you're not there to debate them. And you're looking for clarification, but that you can't help but that influence the way you think then about the work that you do. And so you sit there and, as you say, you interview all of these Nobel Prize winners. I mean, you talk to John Mather, or, you know, they're all just amazing, right? And then you walk away kind of going, I wonder what impact that has on my work. And it's got to have just, I wouldn't be surprised if from the ground up, it hasn't. It hasn't completely changed the way you look at your work. You know,
pitching my second book, which is called Into the Impossible. So these are interviews with the first of the 9 Nobel Prize winners that I interviewed on my Into the Impossible podcast, including Barry Barish, who kindly wrote the foreword to this book. And I realized this is a self-help book, Fraser. It's not a science book. I couldn't resist putting in, you know, a type 1A supernova, you know, when I talk about Atom, and there are, like, amazing illustrations that I had a professional illustrator, you know, concoct. And I'm really proud of it. But what did I do in this book? I tried to distill, I tried to ask the basic question. Can you acquire enough knowledge to become wise? In other words, science, scientia in Latin means knowledge, doesn't mean wisdom. Sapienza, which is like Homo sapient, means wise, or now knows that he knows or she knows. I want to know, if you got to be so smart, you know, could you actually have wisdom? Or could you be like Fritz Haber, the inventor of ammonia and the Fritz Haber and the Haber-Bosch process, et cetera, who then went on to use his chemical engineering skills after winning the Nobel Prize in 1917 or so to witness and personally observe the death by chlorine gas that his factories produced. And then later, the members of his family get annihilated by Zyklon B, which his factory produced as well. And he was a huge nationalist and bellicose guy. Like, he won the Nobel Prize. Like, do I have stuff to emulate from him? But I started to think, like, what would a graduate student, or even like a car salesman in Vancouver, you know, what could he or she learn from a Nobel laureate? And so it has nothing to do with their science. It has to do with competition, collaboration, and especially the imposter syndrome, which I feel all the time. I feel it now.
I feel it. Me too.
You've grown so much. Your channel, I mean, you've like triple, double, like that's kind of like an aspiration.
I don't trust anybody who doesn't have imposter syndrome.
And then on the other hand, Fraser, of course, what's the opposite of the imposter? It's the Dunning-Kruger effect, like
Yeah.
where you think like you learn a little bit and you think you're a genius. I always joke I'm the world's biggest expert in the Dunning-Kruger effect.
So I think that's the
But
gift.
I was shocked, when I talked to Barry, and the reason that he wrote the foreword, aside from him being such a gracious and wonderful individual, co-leader of the LIGO experiment, he told me when he won his Nobel Prize, and you go to Sweden and you accept it and you meet the king and you have some reindeer buffet and whatever. But you also have to sign this book that legally testifies that you got your golden medal and that you got your share. In his case, he got, like $300,000 US of the Nobel Prize $1 million purse or $1.5 million purse. And he said, when you sign this logbook, it's impossible as a curious person not to look back. Yes. Who signed it last year? Who signed it 10 years?
Yeah.
So he saw Feynman. Yeah. He saw, Marie Curie. And then he saw,
that's amazing.
He saw this guy. He saw this guy over here, Einstein.
Yeah, Einstein was in there. Yeah.
Einstein fingerprint. And he said, I'm not worthy of being in the same universe, let alone the same book. And so this is during my interview with him.
Yeah.
And I said, because I asked every one of my guests, and someday you'll come on, I'll ask you this question. I said, what advice would you give to your former self to go into the impossible as the only way of determining the limits of what's possible? Advice to your former self. And he said, to not have the imposter syndrome. I said, you have the imposter syndrome? And he's like, yeah, I have it worse than ever, thanks to Einstein. I said, guess what, Barry?
Yeah.
Einstein had the imposter syndrome. He's like, what are you talking about? I said, he believed that Isaac Newton contributed more to math and physics, but not only to math and physics, to Western civilization, in his words, than he or anyone since. And I said, that's not all. Guess what? Sir Isaac had the imposter syndrome. He's like, what? I said, yes. He lived in awe of a non-scientist, maybe, but a man by the name of Jesus Christ. He felt he was totally inadequate, complete imposter compared to, and I'm sure Jesus felt that way about Moses. You could just keep going down the line, right?
Yeah, totally.
So imposter syndrome, normal, natural. How do you deal with it? How do you deal with collaborating with people who are your competitors? That's a huge thing in this book. How do you listen to things to know you're wrong? Have rubrics to make decisions. So that's what that book is about.
I mean, I feel like that is the gift that I get as a person who gets to interview people, is that you just get to listen. That it's your job to listen and to think about ways to get even more interesting information out of the person that you're talking to. You just can't help but it sort of percolating in. So we're almost out of time. Yeah, go ahead.
Can I stop you? Just one question. I've always wondered from your perspective, you do so many interviews and I try to ape you and emulate you in a lot of ways, but in real time, it would be really helpful to know if I'm doing a good interview. Like, it's very hard to know until
being
you see
interviewed.
No. If like as the interviewer, as the podcaster or host, how do you know when you're doing a good job in real time, if any?
You don't. Yeah, like I think the most important thing for me is just being curious and letting your curiosity lead you and trying to think of the questions that would be popping into the minds of the people who are listening, trying to figure out ways to clarify. My job is to clarify, is to get people to clarify and to explain, their hero's journey as best as they can. And if I think they're being inconsistent, as I might have during this interview, I will hold their feet to the fire for a little bit. But I think it's just important to just listen and be curious and just let the story go and take you where it goes. And I think that people who are being interviewed don't necessarily know what is interesting. Because they're too deep in it, and so they just don't have any perspective. And yet, as a naturally curious person, I find wonder in almost everything that I see, and so I let that be the guide. But I don't know, man. It's just like practice. You know what? What we need to do is it's only fair now. You need to have me on your show.
Yep.
And then we can go into this side of it more in more depth. So
I would love that.
Yeah,
let's set it up. I'll send you a Calendly link this time.
I'm on board. Let's do it. So for people who want to find more information and dig into that rich backlog of amazing interviews. And seriously, like the guests that Brian has on his podcast are astounding. Way more Nobel Prizes than I've ever interviewed. And because you're a cosmologist, you're going toe to toe with these people and you're able to speak their language. And it's been an absolute pleasure in watching what you do. But where can people follow your work? What's the best way to do that?
Yeah, the two main ways are to, my YouTube channel, Dr. Brian Keating. And last year I started doing a short 10-minute thesis, I call it, where I go through experiments. I do experiments in the lab. I've got a video coming out called The Most Expensive Water in the Universe, where I sample different types of water, including some that is made of deuterium and some that is coming from a $50 bottle on Amazon from the Great White North.
Oh, you drink some deuterium?
I drank some deuterated water.
That's awesome.
Deuterium oxide. I drank some Berg water from your neck of the woods up in the glacier somewhere up north. And then I drank, so I won't spoil it, but I drank some water that there's nobody out there listening that could ever get their hands on to very good approximation. I'll explain that in the video. So yeah, I do a lot of short videos, dark matter, but it's from an experimentalist point of view. Excellent. Podcast Into the Impossible is on Apple Podcast, Spotify, wherever you get your podcast. And then my mailing list, as I said, for those of you, I can only ship to people in the US, but I will send a meteorite, an honest to goodness chunk of space dust. See, I got to get your cameraman.
You got to put your, you got to.
There you go.
Well, the problem is that it's trying to focus on your eyes. So as long as you cover your eyes, then the camera will, there you go. We'll focus on
Oh, wow. That's the pro.
Yeah.
Pro.
Yeah. You block your eyes so that the camera doesn't try to focus on them.
So if you go to briankeating.com/list, you'll be entered to win one of 100 of these in the US only that I can ship to you guys. So please do that. And anyone who signs up with the .edu address automatically wins. So I like to give to students.
All right. Well, thanks, Brian. Great to talk to you again, and good luck with all of your research and your work and your writing and your podcasting and all of that. I'm exhausted